Hi everyone, we are Silvana
Valentina, Mariana.
Joan.
and we are Group 10.
Centrifugal pumps play a fundamental role in today's society due to their multiple applications in many industries like cosmetic, agricultural, food, chemical, energy, pharmaceutical, among others. Pumps are composed of a rotating blades inside a case that, because of its rotation, transfer mechanical energy into hydraulic energy, allowing the transfer of fluids at a specific pressure. The impeller's blades are responsible for the rotatory movement of the pump, and their number varies according to the design. The volute is a piece that has the function of converting the kinetic energy of the fluid into static pressure. Besides these two components, the impeller width, blade dimension, attack angles, and other characteristics are important in the process of designing a centrifugal pump. Exist different methods that help in the construction of effective pumps at a specific condition that not only satisfy the necessities and requirements of the client, but also that avoid common problems like cavitation. For the pump design, it was necessary to obtain the efficiency, total head, and brake power curves using 2-degree polynomial regressions for the manufacturer's pump characteristics curves data. The model of the geometry was initially designed in a spreadsheet from the procedure spec by Gulish, which is a preliminary design based on the best efficiency point. In this case, the pump is designed to transport water and mineral oil. The main geometrical dimensions for the impeller, diffusers, and the specifications for the pump are presented in the next table.
After having carried out the design of the pump in Inventor, the result was exported to a STAR CCM program in order to simulate the mechanical behavior of the two fluids, water and oil. However, before carrying out any simulation, it is important to first carry out the internal extraction of the volume and then its meshing to guarantee better results when performing analysis on each geometry. For the mesh generation, we used a polyhedral mesh that generates a more stable, precise, and less diffusive mesh, a thin measure that works for very fine geometries, and a prismatic mesh to improve the precision of the fluid solution. Now, 3 meshes were made through the variation of the base size, coarse, reference, and fine mesh, since the variation of the base size is highly related to the number of cells provided in the mesh. The outlet width of the blade's value was due to the reference for the first base size. The base size of the fine mesh was 30% less than the reference, and the coarse 30%, while the other controls remain constant. After having performed the meshing independence with water, having the results of the number of cells, the computation time for each mesh, and calculating the error of the total head obtained with CFD compared to the manufacturer's head, it can be observed that the error in the reference mesh was the lowest compared to the other meshes, and that the computation time increases as the number of cells is greater. The reference mesh was selected to perform the next simulation because we prefer to have greater computation time than a graded error.
The physical and initial operating conditions that we use for the proper functioning of the pump are pressure 0, velocity 0 as initialization. The reference gravity is minus 9.8 on z-axis, and the reference pressure is 74,660 pascals. At models, we selected liquid and the selected fluid was water. The values of viscosity and density changed for oil simulations. The simulation was done with the reference mesh, which had a base size of 0.019 meters and more than 1 million cells. After generating the mesh in STAR CCM, we ran 5 simulations per fluid, water, and oil, each one with a different value of flow rate as shown below. It is important to mention that mass flow rate must be calculated as flow rate by density over 3,600 to generate currents in units. We assumed that both fluids were single-phase, isothermal, and incompressible. At the end of the 10 simulations, the scenes of absolute pressure, velocity, cavitation, and wave loss were executed to be able to compare the results of each run. Also, reports of efficiency, hydraulic power, mechanical power, total head, and CPU total time needed to be run. Furthermore, we carried out a couple of vector animations where it is observable the development of speed and pressure. Reynolds number was calculated with this formula for water and oil. It's much higher for water than oil due to the physical properties of the fluid, specifically the turbulent flow. In order to find the web flow rate in the group simulation, an efficiency versus Q graph was made up for each of the substances. A polynomial trend line of degree 2 was added, the equation of the line was found, and it was derived and equal to 0. We can observe that both curves have similar behavior to the ideal due to the proximity of R squared to 1.
Taking into account the results of the table, we can see that at the shut-off point for both fluids, it is where the largest head is obtained. However, at this point there is an unstable system since there is no fluid neither in the inlet nor the outlet. The reason why this is noticed is that at this point both of the hydraulic power and the efficiency are approximately 0. On the other hand, it can be concluded that when there are flow rates in range between 90 and 182 cubic meter per hour, which in this case is the flow rate reported by the manufacturer, the efficiency is maximized. This result is consistent with the calculation of the best efficiency point of the design point, since regardless of the fluid, the maximum efficiency was found within this range or is a close value. Additionally, it was found that there is a directly proportional relationship between mechanical power and flow rate. The greater the flow, the greater the mechanical power. This result makes sense since this power refers to the amount of work per unit of time, and the more volume you have, the more work will be required to be able to move the fluid from one side to another.
Now, comparing the results of each of the fluids, it can be said that the efficiency of water is greater in all cases than oil values. As previously stated, the factors that affect the design and effectiveness of the pump are related to the properties of the fluid, such as viscosity, density, and therefore to the models used in the physics. The oil has a higher viscosity and therefore its movement is slower as it requires more hydraulic power. That means more work to be transported from one place to another. For this reason, viscous fluids reach smaller heads as they have a lower speed. Another aim why the power of the water is greater is because as the fluid has a less linear behavior, that means more turbulent, the possibility of creating whirlpools will increase, and for this reason the pump needs a greater effort to transport fluid. On the other hand, the oil tends to have a more linear behavior and therefore a lower mechanical power. Finally, from the efficiency versus flow rate graphs, it can be confirmed that the BEP calculated from the designed pump has the highest water and oil efficiency of 59.8 and 45.7 respectively. Hence, there is not a big difference between our pump's results in comparison with the manufacturers in terms of efficiency, total head, and mechanical power.
In order to visually analyze and make a comparison of how far the data is from the design pumps, such as the efficiency and the head, the following graphs were constructed with the data of ideal case. In both graphs, it can be seen that the most of the efficient and total head data in the CFD model are within the 35% acceptance region. Additionally, the values corresponding of those of the simulation differ considerably from those reported by the manufacturer because one of the points does not fall within the 35% zone. However, the points follow the same trend as the equation y equal x, a linear behavior with a positive slope.
According to the velocity, we can say that in all cases, as the mass flow rate increases, the velocity of both fluids tends to raise. In this case, if the inlet area is the same and if the flow is increased, consequently the velocity of the fluid will increase as well. Recall that the equation is Q equal S by V. There is a direct relationship between these variables. When the flow rate is 0, the velocity in oil is minor than in water. It can be appreciated with the color scale.
The absolute total pressure in the pump has a directly proportional relationship with the flow rate, as it can be seen in the scenes. As the flow rate increases, the absolute total pressure also increases. A lower absolute pressure was evidenced in the mineral oil simulation as well. This could be because the fluid has a lower density. Aside from this, the color bar highlights negative pressure values that indicate suction areas where cavitation could happen.
Cavitation analysis. Cavitation is the phenomenon that occurs in regions where the pressure is below vapor pressure. For the study of both fluids, the vapor pressure was established as the upper limit. For water, 2,339 pascals, and for oil, 4,000 pascals. In this way, it can be seen in the figures that cavitation occurs inside the impeller eye. In this region, due to the low pressure, the fluid begins to bubble. Cavitation is an undesirable phenomenon and should be avoided because it decreases efficiency and it can cause damage to the impeller structure. Moreover, it can be observed that for both fluid cavitation increases as the mass flow increases. Comparing the substances, greater cavitation is obtained for the oil. This is explained from the properties of the fluid such as viscosity and surface tension. The difference lies in viscosity values. In more viscous liquids, bubbles collapse on themselves, causing structural instability. Now considering the figures of wall Y+, it is observed that for both fluids and all mass flows started, we was obtaining a value between 0 to 5. This occurred because the logarithmic function can correctly approximate the behavior of the fluid. However, for oil, Y+ take values around 0 for most of the surface, while water takes values in entire range of 0 to 5. Conclusion. We can conclude that to obtain a centrifugal pump that satisfies the needs of a certain consumer, such as efficiency, height, mechanical power, hydraulic power, among others, it is necessary to evaluate certain parameters that influence the pump. The most important to take into account are the mesh independence, the geometry, the model used, and the properties of the fluid study. The general result of this project allowed us to conclude that cavitation is present for both fluids in the impeller eye, an event that occurred due to a lack of smoothness in its geometry and to its effect it wasn't possible to have a higher efficiencies. In the mesh, the values of Y+ for the recommend while were fulfilled since the simulated fluids showed values below 5, which allowed a good approximation of the model. It is important to highlight that the Y+ must always be below 5 or above 30, since in the buffer region the curve don't give a good fit of the system. For this reason, it is known as a transition region and it isn't recommended to place any cells in this zone. Comparing the head and efficient results between the manufacturer and our pump, which studied 5 flow rate per fluid, a maximum error range of 35% was found. On the other hand, the manufacturer's pump was designed for the use of water. However, the results have shown that it is impossible to use it to transport oil, although lower efficiencies are obtained due to the specific properties of the fluid. Another conclusion would be that both velocity and pressure have a directly proportional relationship with the flow rate in any studied substance.